Yeah, hello to this short video summary of our new paper, Cluster Sizes in Subcritical Soft Boolean Models. And let's start with the model. So the soft Boolean model is a continuum percolation model. That means we build an infinite graph on the points of a Poisson process in Euclidean space, here Rd. And to connect the vertices and finally build our graph, we do the following. So first, to each vertex of the Poisson process, we assign a Pareto distributed radius with some tail exponent 1 over gamma, where gamma is in between 0 and 1, so that 1 over gamma is always larger than 1, and the radii have finite first moment. And the closer gamma to 1 is, then the more heavy-tailed the radii are. Additionally, completely independent of the radii, we also assign to each pair of vertices, that is each potential edge, another Pareto distributed random variable, which we call the edge weight, W, which is also Pareto with some parameter delta, and which is also larger than 1, so also finite degree, and, not finite degree, finite first moment, and the closer delta is to 1, again, the more heavy-tailed the edge weights are. And the finite first moments of both of the Paretos then in the end leads to finite degrees in the graph. And that's what we want, to remain sparseness. And given the Poisson process, the radii, and the edge weights, we then connect each pair of vertices precisely if the distance to the power d is smaller than some edge intensity parameter beta times the edge weight times the larger of the two radii. So it's easy to see that beta is indeed an edge intensity. So if I increase beta, then this threshold on the right side gets larger. So I add more edges, or contrarily, if I decrease beta, then I make the threshold smaller, and on average, I remove edges. Also, the to the d on the distance is here so that my Pareto or my model parameter remains independent of the dimension, but you could also bring it to the other side and build it in the Pareto indices. But let's not do this. So if we have a look at the picture here, we see that the soft Boolean model has two effects. We can see long edges, but also heavy-tailed degree distributions. Heavy-tailed here means I see stars which are much more connected to neighbors than maybe on average. So I have two main effects, long-range edges and the heavy-tailed degree distributions. And so let's have a look at the single effects, namely if we send gamma to 0, that means basically we take the radii out of the game. Then we observe a version of the classical long-range percolation or random connection model. And here we see we still have long edges, but we don't have heavy-tailed degree distributions. And conversely, we could also send delta to infinity and recover a version of the soft Boolean model. Here we don't see long edges anymore, but we see the stars again, so the heavy-tailed degree distributions. So in a sense, the soft Boolean model precisely interpolates nicely between the two standard models of continuum percolation. And now we're interested, if we combine those two effects, the long-range edges, but also the degree distributions, the heavy-tailed ones, how does the model behave? And as the title already suggested, we want to do it in a subcritical regime. And that means our edge intensity is small enough so that all connected components in the graph is finite. And first of all, is this possible? Yes, it is. At least if gamma is small enough. So if gamma is smaller than 1 minus 1 over delta plus 1, so let's say the radii are small enough compared to the long-range effects, then the critical percolation intensity is indeed positive, and we can choose small enough beta to only see finite components. And in such a component, we now are interested in what are the typical sizes. And we have two quantities in mind. Firstly, m, which is for us the Euclidean diameter, that is, in the component of the origin, which plays the role of a typical component, is the vertex in this component with largest norm. And again, I take the norm to the d here to not have the dimension in my results later. And the other parameter we are interested in is n, which is just the number of vertices that are contained in the origins component. And if we choose such a subcritical regime, then we have two phases for the Euclidean diameter, namely if gamma is very small compared to delta, let's say, then we observe a heavy-tailed Euclidean diameter with an exponent 1 minus delta, which is independent of gamma. But if gamma is larger than this threshold, then we observe a heavy-tailed Euclidean diameter where the exponent depends on both effects. So here really both effects mixed and matter. On the contrary, if we take a subcritical regime but gamma smaller than a half, which translates to finite variance degree distribution, then for the cardinality of the component, we observe still a heavy-tailed one, but with an exponent that only depends on gamma. We could prove this for gamma smaller than a half, but we are very certain that this is true in the whole subcritical regime. And so let's shortly play the game from earlier again. So first, let's send gamma to 0. Then obviously on the left-hand side, we end up in case A, and we observe just the result from long-range percolation, which is already known. On the right-hand side, well, if we send gamma to 0, then the exponent becomes infinity. So again, as we know from long-range percolation, we find a light-tailed cluster cardinality. On the other hand, let's send delta to infinity now. Then, of course, we are on the left-hand side on case B. And actually, we observe 1 minus 1 over gamma in between as a result in the exponent, which is precisely the exponent of the right-hand side. So here, as known for the Boolean model, we recover the known result and actually also see again that both results actually are of the same order, or both quantities are actually of the same order. So as a boundary cases, our result gives us the classical result, but now we can see how both effects play together. Namely, the additional long-range effects and long-range edges really helps to enlarge the Euclidean diameter, but they do not help us to collect many more vertices in the component. So basically, except for constants, but the order of magnitude of the vertices, which are in the connected component of the origin, remains the same as for the classical Boolean model, but with the additional long-range effects, the furthest away vertex is much further away. And to quantify this, here's our result. And if you're interested in how to prove that, or have more comments or questions and other input, please just write us an email. Thank you for taking your time to watch this, and I hope I motivated you to have a look in our paper. Thanks a lot.